So our next speaker is Håkan Engqvist from Amplicon. Thank you, Håkan.
So, thank you. So, well, thanks. Perfect. Like that. Feels like a politician. Okay, anyway, so my name is Håkan Engqvist. I come from Uppsala. I'm a professor in applied material science at Uppsala University. And I'm one of the founders and inventors behind Amplicon and the product that we will be talking about today. So, let's see if it works. No? So what we are working with is controlled release of nicotine. So first of all, we're working with a white pouch. Today, the release of nicotine is mainly controlled by the solubility. So if you have a salt and you mix it into liquid, the release of the nicotine is controlled by the solubility. And this leads to that the size of the pouch also controls the release profile. So you might have seen the normal white pouches. They have a specific size, and then you get the nicotine release. If you reduce the size even further, which is beneficial, for example, for new markets and also for with the dry, compared to wet and the dry ones. Okay, so the small pouches are wanted in non-traditional snus markets, but when the pouch are small, the release is very quick, and also the flavor goes away really quick. It's like the chewing gum with and without sugar. Okay. So what we have been working is a way to control the release of nicotine. And what options do we have to do that? I do understand that there are ways to work with actual nicotine molecule and thereby control the release, the solubility of it. Otherwise, there are the options to work with the polymer technologies. Myself, I'm a ceramicist. So I do ceramics in my research. So we have been developing a method to do controlled release of active ingredients, and in this case nicotine, through bioceramics. So the two options that we could foresee is to use the traditional polymer technologies, which is more cumbersome to use if you would like to have it in the oral cavity to control because then the actual polymer would need to be dissolved in a very rapid manner, which is difficult. So what is a bioceramic? So ceramics in general are known as oxides. The earth crust, more or less, is based on ceramics. So it's oxides, nitrides, or carbides. But also cements. That's what it's called in chemistry. It's called chemically bonded ceramics. And they can be found naturally. Our own hard tissue is a cement, chemically bonded ceramics. It's called hydroxyapatite. So it's a composition with calcium, phosphorus, and hydroxy ions. And traditionally, or science history, the Romans were the first one who learned how to handle cements when the Roman Empire was at its prime. So I would say maybe around 30, 40 years ago, the cements were taught to be handled also not only for construction, but also for biological use. And in that case, it's used for hard tissue replacement. Bone void fillers are normally cement-based. So what we do, so we come from that cement chemistry, and we work what is called the calcium salts. So we work with the calcium salt. Here I denoted a bioceramic. So we mix the bioceramic with water and could be bulk agents or what we call fillers. It's similar if you would do concrete at home. You take 1 scoop of cement and 3 scoops of sand and you mix it with water, you get a cement paste. We do a similar, but with a bioceramic instead. And then we add nicotine into the mix. So we have a paste containing nicotine and bioceramic and water. And then we let that set and harden. So it hardens into a hard lump, which we then crush and sieve into the desired size that we would need. Okay, so depending on the size, we can control the release, and then also depending on the choice of these ingredients, we also control the release from relatively fast to very slow if needed. And the end, when it sets, now it's exaggerated, but it formed like a Swiss cheese. But the pores in these, the pore system is what's called from a few angstroms up to a couple of 100 nanometers. Depending on how it's made, it could also be air voids by the mixing technique. But naturally, it's in the nanometer to angstrom range. And within those pores, the nicotine, or the active ingredient, is. So when placed into a pouch, the release mechanism is by dissolution and diffusion out of the pores. So the pore system controls the release mechanism. Okay? And so in comparison then with what we are trying to achieve, so let's see if I can do this. The upper curve is the controlled release mechanism, and these two is from a conventional dry and a conventional wet white pouch. And we are closing in to having a constant release. We have what's called the first order release of the nicotine. And why is this beneficial? Yeah, because the release we foresee, we do not have PK values, but when you have this rapid immediate release, much of the nicotine is actually swallowed, and the bioavailability is less. If there is a more constant release, the experience is the same, and thereby we also have a longer effect of the same amount of nicotine. If you follow, yeah. Okay, and the same goes for the taste, the flavor. The flavor also go into the system, even though at the moment we don't have a good measurement method for flavor, just by taste. So the taste follow the same experience. So what we have, it's a completely new release profile, and we claim that it's the world's first dry white nicotine pouch with fully controlled release of taste and nicotine. The dry white nicotine pouches for consumers, adding completely new release profiles and experience, targeting the large and growing global market for nicotine pouches. So we then say this is the next generation of nicotine pouch. It's a small. We do them small, but the same effect as from the bigger ones. We can customize the nicotine delivery even further than what I just showed. And by this, we can also then have the release of the flavor to be tailored. So for example, we can have a fast release of nicotine, long flavor. Yeah, you understand. This can be mixed in many variants. One thing that I haven't mentioned that much was the pH stability. Calcium salts, not all of them, but most of them are alkaline by nature. They contain the calcium, and so the pH is normally within these above 7. There are a few that are acidic, but that's a few of them. The production that we use, it's scalable, just normal ceramic production manufacturing, I would say. And we do have, well, we claim that at least, we have a strong IP with freedom to develop and to be even more innovative. So our initial target markets is the non-pouch markets, Europe, Japan, Korea. And of course, in the existing oral pouch markets, the urban ones, new users, women, and vapors. We are still working on the branding and profile. We have the booth outside. Some of you might have been there already, and please come and talk to us. And we have, get some more information there. And so we represent the first dry pouch with long-lasting diffusion of taste and nicotine. Thank you.
Thank you, Håkan. Questions? Oh, gosh. One there.
Thank you. The ceramic, it is polar, non-polar. What is the electric nature of what is the binding capacity or the binding electricity matrix that is created by the ceramic in terms of being able to, let's say, put certain flavors components in it?
The flavor components would go into the pores as well, as long as they are water soluble. If there are, it's difficult for us to do when there are non-polar. If you see what I mean, if they're not soluble, we need in this process. When we do this in the process, we do like things that are water solubles, because then it goes into the mix and into the pores. Otherwise, it will be similar as the normal white pouches. The more those that are non-soluble.
Thank you.
I think there's another question behind, and then we'll come over to this side.
Thank you. Mark McQuillan, Nicobrand. Two questions. It seems that you have substituted MCC for this ceramic material. How does that compare in terms of, let's say, cost of manufacturing compared to conventional MCC? And also, what form of nicotine are you using in your pouch formulation?
Yeah, so there were two questions. So these raw materials are relatively inexpensive. MCC is also very cheap in a way. So I'm not saying that we're lowering the cost of goods, not at the moment. Big scale, maybe. At the moment, no. And what was the other question you asked?
The other question was what form you're using a nicotine salt, free nicotine, what is it you're using?
No, we're using the salt. The nicotine salt, yes.
And over here on the right, thank you.
Yes, thank you, Rafi Castillo, Philippines. It's really a very interesting mode of nicotine delivery. How is the sustained release in terms of pharmacokinetics, comparing it with, for example, transdermal nicotine release? Does it have a pulsatile release of nicotine, which transdermal lacks, and is implicated as a reason why it cannot be that successful as in terms of replacement therapy? So how is its pharmacokinetics? I think the crucial factor there is if it enables a pulsatile release of nicotine, which can really satisfy the cravings in smokers.
Sure. So what the data we have at the moment from bench studies release, and then just by panels. So I don't have a PK study to show you from. So we need to do that. We haven't done that yet. That's on our list to do for the autumn. So,
okay. Thank you.
Oh, there's one down the front here. Oh, if you see. Question at the front. Do we have a microphone? Thank you.
Good afternoon. Tom McGrath from Switzerland. I don't know if you have the data, but do you have anything yet on shelf life and aging of this product?
Yes, we do have, and so far, so we have, of course, it's an ongoing study for us as well, but so far, it seems to be very good when it comes to the shelf life. We do believe it has to do with both the incorporating of the nicotine within these pores, that it becomes more stable, but then also the pH stability is inherent in the system. I would also mention that there is a calcium release from this, from the ceramics. I mean, they are used as biomaterials, so it interacts with the saliva as well. Okay.
Kent from Denmark. Did you compare your material with other mesoporous silica, for example, or other porous materials?
Yeah, we have that tradition with other APIs, with more pharmaceutical-based ones, yes. And there we have one benefit that I didn't mention. It's the loading. We know exactly how much we load. With the other, the porous silica and all of these, there is a drip technology, or they should be soaked, and it's not that easy. It's very difficult, not easy, I would say. It's very difficult to afterwards know the loading, how much did you actually get in there if you're going to soak? So I know that by other projects, let's say, it's a nightmare to characterize those materials. You could load and get it out, but it's more difficult from a quality assurance. In our case, it's easy. It all goes in there and is well distributed.
Okay, any other questions? I'm looking, it's very difficult with those lights in my eyes. You have to really make yourself known if you want to ask a question, I'm afraid. Okay, I think...
And there's one more.
Oh, there's...
Oh, over there. Oh, two.
Back to me again, Håkan.
Yes.
On your the information you presented there, the release profile,
Yes.
Could you give us some more details in terms of the reference products that you used for what you called your conventional white products, and again, whether these were salt-based products, free nicotine products, strengths, that type of thing, and also how was the release performed? Was it in vitro, I guess, somehow or other?
No, exactly. No, we can talk afterwards, perhaps, about that. No, it is just a normal release study done on conventional white pouches, the one that we compared with, that are commercially available.
Okay, and there was a question at the front.
Sorry for coming late. I was in a board meeting with Inco. I'm Bengt Wiberg. I just have 3 simple questions. I read your folder. The 3 questions are, what is the weight in grams, so to say, per pouch? And the second question, what is the pH level? And what is the rate of free nicotine?
Okay. So the pH level we can control depending on what type of ceramic we choose to work with. At the moment we are around 8, but we could lower or higher it depending on what type of system. Free nicotine, what do you mean with free nicotine in that case? How much that is bonded within or outside?
The percentage of unprotonated nicotine is depending on the pH level. So white fox pouches have a free nicotine level of 98%. I think like Lift or Velo has free nicotine of some 65%.
No, I don't have that data, so I cannot answer on that question. And the weight that we chosen to use is the same as with others. Of course, we reduce it in the smaller pouches. We have tried different ones.
What was the weight per pouch? What was the weight per pouch?
About the
0.3 gram. Thank you.
Yeah. But the density of this is of course much higher than the previous question about the MCC. This density of this powder is around 2.5 roughly. You know, the density, whereas the MCC. So the volume gets less. Yes. You get that. Okay. Yeah, because it's like a stone. Okay.
Okay, I think that's that. Thank you very much for taking a range of questions there. Thank you, Håkan.
Thank you.
Oh, sorry.
Thanks. Sorry I was a bit late there. It's David Lewis from Cambridge Design Partnership. I was interested in how you've evaluated the market potential for the technology and the product. Have you done much user research or evaluated how it would resonate with potential users?
No, that's still, I mean, not more than from general knowledge about the market. We haven't done any specific by our own market research in these new markets, more than what is kind of general knowledge within the field of what would be used and not used, you know, the next steps. So we don't have that.
Okay, I think we will let you go now.
Okay.
But thank you very much, Håkan.
Thank you.